of the base angles, keywords, of an isosceles, another keyword, triangle, has a measure that is 30 less than the measure of the vertex, another keyword, vertex angle. Find the measure of each angle. Okay, find the measure of each angle. Now, you might not have seen this in 1.8, but what we're going to start doing in section 1.9 is using what are called let statements. Has anybody been introduced, or is anyone familiar with let statements? Okay. So does somebody want to give me an example of why you might use a let statement? What's its purpose? Katarina?
So that you know what you're representing X for, so that when you finish solving, you're not confused with it.
That's exactly right. Well done. You know what X represents, or Y, or Z, or whatever you want to call it, right? Doesn't matter. It's a variable. So we know what it represents. Now, at the end of the problem, we can go back and figure out, well, what do I have to do with it? You know, do I have to take that and plug it back in for X? Or do I have to do X minus 30 and such? So we're going to go through this. So, what might help this kind of a problem? What might assist you? Before you even begin with the let statement here, what kind of a problem is it? And it's tough because you haven't taken this class yet. It's a what? Let an inequality. Like, why do you think it's an inequality? And I understand what you're saying, so just explain this so we're all clear. Yeah, when you see less than, you want to think inequality. We all agree that less than, you think inequality? And I agree with you too. Now, the only reason I would say it's not is because it says 30 less than the vertex angle. So if we define the vertex angle as some variable, then we just have X minus for less than. But I understand what you're saying when I see less than. That's a good point. What kind of a problem is it in the sense of types of math problems? We have a triangle, so what kind of a problem? A geometry problem. Now, you haven't taken geometry, right? It's next year. But you do know your basic laws of geometry. Okay, you've learned some of it. Now, what does isosceles mean? Anybody know that one? Remember that from middle school? Karina?
I think it's when two of the sides are equal.
You're absolutely right. Where two of the sides are equal. So what we're going to do is draw a triangle such that it looks like these sides are equal and the base is different. And I know this is new because you haven't taken geometry. You did take, your basic 7th and 8th grade math, which included some prior knowledge of geometry, but not as much. Now, with that said, I'm given a relationship. That's the whole key of math. You're given relationships. And you're told that the base angles, that's plural, right? So how many are there going to be? 2 of them. Because we have 3 angles total. This is considered the vertex angle, and these are your base angles. Your base angles. Now, with that said, we want to think about how we can label this appropriately. Okay, how can we label this appropriately? So let's look at this diagram. What can I call the vertex angle? Like, why the vertex angle X, Michael? Because we don't know what it is. Good. And we're told something about the base angles, aren't we? We're told the relationship between the base angles and the vertex angle. What is that relationship? What is it? Be careful. Good. Okay? You gotta slow down there. It says that the measure of the base angles is 30 less than the vertex angle. Well, if we say let X equal the vertex, which is what we're doing in our diagram also, then this is 30 less than that. So we take 30 away from whatever this is up top. Therefore, this is X minus 30, and this is X minus 30. What should I put as my units for these quantities over here? My units. Degrees. Very good. Degrees. Okay, degrees, please. Now, I've got a let statement. Do I need the other let statement, really? Sometimes teachers tell you, they'll say, let X minus 30 represent the base angle. But we showed that in the diagram now. Do you see this? So this is like an alternate form of a let statement. If you didn't have a diagram and you wanted to define X minus 30 as a base angle, that's fine. But then it's kind of redundant to draw the diagram also. Okay? So if you have this, you're good to go. What do you know about the sum of the interior angles of any triangle? They equal 180. Very good. 180, what's the units there again? Degrees. So I can put degrees here, and degrees here, and degrees here, and then degrees on the 180. But if they all have degrees, don't worry about it with your algebra. Is that clear? Okay, later on, when you give an answer, you want units of degrees. But for now, since X already has the degrees, or just solving for some quantity x. So we take that, we add the x minus 30, we add the other x minus 30, and we set that equal to 180. Understand what I just said? You don't need to do this. Okay? Once you do this enough, I encourage you to not write x minus 30 twice, but to simply do this. I'm doing this to show you, but again, you don't need this here. Just put a 2 out front, and we can use our distributive property because there are 2 base ends. So I've got x plus 2x minus 60 equal 180. Again, what did I do here? Make sure you distribute this to both terms. Don't forget this negative here needs to be carried down. What's my final step? What do I do at the end here? Good. So we got 3x here. What do I do with the 67? So what does this become?
2.
Good. Because 18 plus 6 is 24. Do these here in your head, please. And we get, Erickson? 80. Very good. So, Erickson, is that the answer? 80 is the answer? Are we done?
No.
What do we have to do now?
Yeah, please subtract 30.
Good. To make a statement, right? So, whenever you have a let statement, you also need a conclusion statement. Because you don't know if you're just solving for x here, right? We don't know that it's just x. We're finding a measure of each angle. Each angle. How many angles are there? Everybody? 3, right? 3. Triangle. Triangle is 3. So one of them is 80. That's x. So go ahead and put an 80 in here so you know what you're doing. And let's put in degrees here now where they have other angles. And what do we got for the other 2 angles? Pretty obvious, Nick? 50 and 50. Very good. Okay? Now, if you're taking a test, you should probably write it in words. So can somebody give me a statement they would say to describe the scenario we have here? How would you describe the scenario? Jules? Perfect. The vertex is 80 degrees, and the base angles are 50 degrees each. Let's say each, make sure. Okay? Is that a pretty easy problem? Right? Okay. This should be a pretty basic one. We're going to get to a little more complicated ones in a minute. But again, I want to get going to start with geometry so you can see it. Okay. Number 2. We're only going to do 4 problems. Okay. We're only going to do 4 problems. For number 2, I'll dictate. You're welcome to write it all down. You're welcome to write down whatever you think you need. Again, the notes are online, so you're welcome to always go back and see what the actual wording is later. But I'll dictate. Adults tickets for the art museum cost $1.50 more than children's. So right away think, adults cost more than children, which makes sense. Whenever you go to the theater, right, if you're a senior citizen or if you're a child, your ticket is reduced. One day, 200 adult tickets and 160 children's tickets were sold at the museum. The income from the adult ticket, the adults' tickets, rather, was 30 less than twice the income from the children's tickets. How much does each type of ticket cost? So we're given a bunch of info, and we're pretty much set told, find the cost of each ticket. Okay? Later in the year, we're going to learn about something called systems of equations. And there is another way to do this problem. Today, though, what we're going to do is we're going to do our standard algebraic way with lessons. Okay? And I'm going to actually revisit this exact problem in about 4 or 5 months from now when we get to the other topic. Because there's another way to solve this. So, matrices?
Yeah, maybe.
Yes.
And like,
You line up the x's, line up the y's, line up the constants.
it's like X and Y.
Yep. And it could be x, it could be any amount of variables as long as you have that many equations.
Yeah.
So 20 variables, 20 equations. You can solve. Correct. You can put it in row reduced echelon form, which puts it in like ones down with diagonals and zeros in all the other spots. It's another way. You can use your calculator to simplify. You can use something called Cramer's rule. There's many ways to solve. We're going to get to that. Good question. Eddie. Go ahead.
No, like, I was going to say, would this work if we were to, I feel like 2x minus 30 equals 200, and then above it for the adult ticket, I put 150 plus
minus 30?
equals 200 if that's the amount sold. So
No, because where's the 2x coming from?
no, because the price there is double the amount of adult tickets sold.
Oh, I see that.
Minus 30.
No. Let me explain, hold on, just because I think it's the let statement you're forgetting about. We start with the let statement, it might make it a little bit easier to see what the equation is. So, just for 1 second, hold that. We see that we're trying to find what? The cost of each type of ticket. So, which ticket costs more? The adult. The adult ticket costs more, right? How much more is it? $1.50. So if the adult ticket is $1.50 more, I can start by saying let X represent the cost of a child ticket. Okay? Let X represent the cost of a child ticket. Since we don't have a diagram, I should really define my next statement also, even though we didn't do 2 let statements last time. But what would I go for the second let statement, Summer?
X plus 150
Good.
equal
Now, if you did this with systems of equations, you would use X and Y. You would say let X equal the cost of the child ticket, let Y equal the cost of the adult ticket, and you would use two equations, 2 variables. But for today, for the purpose of the topic we're on, we're going to continue to use a relationship between 2 different quantities, okay? Both having X. Now, if I know the cost of each ticket, I'm also told that 200 adult tickets were sold and 160 children's tickets were sold. Okay? I know that the income from the adult tickets was 30 less than means subtract, less than twice the income from the children's tickets. So we've got a lot of stuff going on here. Let's say hypothetically. Let's say the adult tickets cost $2 each. Hypothetically, not the way. $2 for an adult ticket. How many adult tickets were sold? What does it say? Okay, 200. So what would the cost be for the income from adult tickets? 400, right? You take 200 tickets, and if it were $2 for a ticket, 400. But in this case, we don't know. We don't really know the cost of each adult and child ticket, right? We have some sort of algebraic representation. So if I want to know the income from an adult ticket, I have to take the amount of tickets, 200, times the cost of an adult ticket. So I start by saying right away, 200 parentheses X plus 1.5. This would be the income from an adult ticket. Again, here's the cost. Here's the cost of the adult ticket. Here's how many were sold. Now, the problem goes on to tell us that the income from the adults' tickets was 30 less than twice the income of the children's tickets, which is really worrying, isn't it? What is the income from the children's tickets? What would that be represented by, the children's tickets? 160 tickets, go ahead. And what does each one cost, man? But let's say variables then. No, look at our last statements. What's the cost of a children's ticket? Sure, that's fine, but we have a relationship here. Look at your last statement, man. My question to you is this. What did we define as the cost of a child? X. Again, the cost of a child ticket is X. It's X. So if we take 160 tickets times however many or however much each ticket costs, this will be the income from the children's tickets. But we are told that the income from the adults' tickets, right here, is equal to 30 less than twice the income of this. Again, I'm going to read the statement, write it down for now, and I'm going to give you a second, and then I'll read through it to show what I mean. Because this is a very confusing problem. So, on the left-hand side, 200 tickets for adults times the cost of an adult ticket. This gives us the adult ticket income. I'm going to say the adult income. Okay? Next, this 160X is the children's income because 160 tickets were sold and they cost X dollars each. But we were told that the adult tickets, the income from the adult tickets was 30 less than, that's right here, 30 less than, twice the income from the children. Twice, this is the 2 here, the income from the children. Okay? Again, it's a very complex problem to solve this way. Once we get to systems, I would recommend we solve with systems, and it's a lot easier actually. Okay?
I
Summer.
have a question. If it was a system, what would be X and what would be Y? Like, if
X would be child,
yeah.
Y would be adult. You would say X equals Y minus 1.5. The children is the adult minus 1.5. Then you would say adult cost times 200 equals or twice the children's cost minus 30. That would be your first equation. That would be your second equation. You have X and Y, you would solve those. Okay, that would be your system. And in this case, I would use substitution method. And personally, I would take the definition of X right here and substitute it in right there. But now, if you did that, sorry, not there, over here. If you did that, you would get the same equation, it turns out. Okay, it would look different, but you get the same equation. All right, at this point in time, what's the last step? What do we have to do here? What do we have to go through? What process? So,
200 times X, and then 200.
what's 1.5 times 200?
300.
Good. By the way, that's a 200x here, 200x on the left side. Right there. Equals, now we got 2 times 160 is what? 2 times 16 is 32. 320. So replace this right away with 320x. Okay, 320x. So we know it's 320x minus 30. Questions so far? I know this is complicated. These kinds of problems, the only thing that helps, honestly, is just doing more. The more you do these, the easier it gets. And especially when you start doing like, if you take classes like calculus and physics, these are the kind of problems you look at. And once you take those kinds of classes, this is probably like, Ned is probably like, yeah, this is a normal kind of problem, It's the kind of stuff you see all the time. And it gets easier as you go along. All right, so at this point, let's just solve. I'm going to move the 200 over because I'll keep the positive x quantity, and I'll move the 30 over here. This becomes 330. Everybody clear with that? We got 330 there. We're going to have on the right-hand side, 200 from the 320. We're going to have 120 x. God bless you. Okay, again, what am I doing in case you're wondering? I'm taking this, subtracting it over here to make us 120. I'm taking the negative 30, and I'm adding it up to 300 to get 330. Divided by 120, you're going to get $2.75. And notice I put my units there. Okay? But the problem said what? Find the cost of both tickets. Good. So hey, what are we going to do at the end here? I got X.
Minus
Let's go back and figure that out, actually. You sure about that? I think I might want to add $1.50. Because $2.75 was the cost of the child ticket, right? Who said that earlier? Katarina, right? Isn't that why we define X? So when we go back, we know what we're talking about. So because X was $2.75, that's a child ticket, so add $1.50 to that to get the adult ticket cost. Okay, so this is the children's ticket, so then we say X plus 150 is going to give us $4.25. So if you want to make a little summary, adult ticket is $4.25, and child's ticket. What does that mean when I put 2 little quotes below the previous line? Peter? John? Okay, very good. Same thing as the previous line. So I didn't want to write the word ticket again, so you put little quote marks. Sorry, guys. Okay. All right, let's go on to the next one. I think this is another good problem. Take a look at it. I'm going to read it to you, and I want you to think about and draw what you see. And I want you to draw it on your paper. This is going to be another geometry problem. You see it right away. So we got this guy Bob, and Bob's a city planner. So a city planner pretty much organizes the orientation of the city. He or she might be in charge of making a new park or designing a new square in town, whatever it may be. So Bob has two pieces of metal wire of equal length. He shapes one piece into a square to represent a new building site, and the other into an isosceles triangle to represent a nearby park. We're told that the base of the isosceles triangle is 4 centimeters shorter than the side of the square, and each leg of the triangle is 9 centimeters longer than the sides of the square. And how long is each piece of wire? And how long is each piece of wire? So I said to start drawing. So what would you draw here? You can tell me what shapes I'm going to draw right away.
Square and a triangle.
Good. What kind of a triangle, Edward?
Isosceles.
Good. We know a square has equal lengths and has all right angles, correct? So all these sides here are equal lengths. Then I draw myself an isosceles. And I'm going to make sure I exaggerate it so I know that I have two equal legs and then a base. Okay? Just like earlier, we had two base angles and a vertex angle. Now we're concerned with the two side lengths here and the base length. But I'm exaggerating it to show you that these are equivalent. That's the whole idea of isosceles. Okay. Now the next part is a little tougher. I want to think about here what my let statements will be. And that's the hardest part. You got it ready yet?
No, I was gonna fill in the side.
That's fine. That
Uh,
works. That's like the let statements.
oh, the base is x minus 4.
What's x first though? We can't.
X is the side of the square.
So you just made a let statement, didn't you? Let x equal the side of the square. So a minute ago you're like, no, I'm not going to do let statement. We're filling the sides. It's the same thing. Okay? That's what I want you to see. So by putting x here, you're already making a let statement in that says let x equal the side length of the square. Continue.
X minus 4 at the base.
On the sides.
And then 9 plus x.
Good. I'm going to say x plus 9 to be consistent. Okay? Because I want to remember that if it's subtraction, I can't switch the order. So let's be consistent. Obviously, addition is commutative. We can switch those if we want to. At this point in time, what do I do? I can saw half a hand. I think you want to answer.
No, that's fine.
But what does it say? Nick? Tell me. It says that it says two pieces of metal wire of
Equal length.
so
Overall, the square of the triangle the perimeter is the same.
very good. And I like the way you use that word. You didn't say they're the same because they're clearly not the same, right? These are not the same shapes, but their perimeters are equivalent. So tell me. Go ahead, Nick.
I would do 4x equals 2x plus 14.
Very close. How about 3x? Okay.
Oh, 3x.
Let's
Sorry.
go through this. That's all right. We're good. So we got 4x's, right? So the perimeter of the square is this 4x right here. Add up these three terms now. X plus x plus x gives us the 3x right there. 9 and 9 is 18. 18 minus 4 is 14. Okay? So what have we done? We've said, and this is how you would write it, perimeter of square equals perimeter of triangle. That's a p with the subscript of x. Perimeter of the square equals the perimeter of the triangle. That's the equation we have here. Notice I really didn't make a let statement here. I didn't really make a let statement because, as Edward showed us a minute ago, the diagram itself was my let statement. Okay? Continue, Nick.
X equals 14.
Good. And notice this is an easy one, isn't it? Once you get the statement done, 3x and 4x, that's so simple. Subtract from both sides, you're going to get x equals 14. Are we done?
No.
Why are we done?
Continue to figure out the overall perimeter.
Good. Now, notice, the problem doesn't say to find the lengths of the sides of the triangle or the lengths of the sides of the square, but it says to find the length of each wire. How long is each piece of wire? So do I want to go back and plug it in over here in this complicated one? Right? Use logic. Save time. This is more complicated than this is. So you have 14. Just think, 14 times 4, what is it? 56. So each wire is 56 centimeters long. We're done. There's no need to go back to the triangle. You can go back to the triangle to check your answer, to make sure logically, and it works. If you try 14 here, you're going to get 23 plus 23, which is 46, plus 10, which gives you 56. So both shapes are 56 when you have a length of, or an x value of 14. But again, this part doesn't really matter. It's this part that's important. And when you're taking a test like an SAT, this is the kind of problem that's on those tests. So when you get the answer of 56, after you plug it in here, you're done. If you have time at the end, what do you do go then? Then you go back and check. Remember, that's like the only time you're going to hear a teacher tell you, go through the whole section first, then go back and check your answers if you have time remaining. If you want to get to 800, if you don't do the problems, you can't get 800. You can get one wrong or leave one blank on the SAT and still possibly get 800. And that's a rare occasion. It has to do with normal distribution and how the grades are skewed for each test. But for the most part, if you want to get a score that's real high 700s or 800, you need to get it proper right. So you need to manage your time quick and efficient. Okay? Any questions?
For our test on Friday, how much work will we have to show?
For a problem like this, that is more than sufficient what we've just shown you. You have to show your steps. I mean, if you get a problem right by doing your head, it's all right. It's not the end of the world, but it's a good chance that the problems in the test are not going to be ones that you can do in your head. Remember the one we did with the number line, where you have to find the location X, and there's 1/3 from A as far from B and such? Doing that in your head might work in class sometimes, but I'll tell you now, I'm going to make them so they're decimals. So you can't just do it in your head. So you have to do the work. Okay? So I'm not going to make it so that you can just say, oh, I get it, it's 7, or oh, I get it, it's 5, you know? Okay? So those kind of problems you can do a little bit tough.
Are we gonna have to show two on that, or are we gonna have one?
Are you going to have to?
The number one. Do
Should you
want-
show the number line on it?
No, do you want us to have one or two answers? Like,
Well, if it says find the coordinates from the parentheses out, you have to find all that work. And that might be multiple choice. Maybe I'll give you multiple choice for that problem, and you have 2 possible answers for each choice. We'll see. I haven't made the test yet. I'm thinking about it. So, I'll tell you now though, just to give you a little preview, okay? It's going to take you a full period. It's not going to be as hard as your future test, just because a lot of the stuff we've done is review. The difficult part, I think, of this test is going to be remembering, like, you know, commutative property, identity, and multiplication. But I'm only going to give you like one of those examples, just so you know. I'm not going to give you like 10 of those examples where you have to fill in the property of every step. Because if you get it wrong once by accident, you're not going to, you know what I mean? It's like double jeopardy. So I'm going to give you one of those problems for the most part. And the other problems will be from each section accordingly.
Do you get parking credit? Because I know some of my math teachers like did not, and then it's like my last one. You get what's in your pocket.
It depends on the problem.
Yeah.
I'm going to give part multiple choice and part free response. If it's multiple choice, there's not going to be partial credit because I'm trying to like mimic the SAT and standardized tests. And if you take any sort of AP test, you'll be told, and your other classmates will tell you, you get multiple choice, which is no partial credit, and then there's free response, which is. So we're all mimicking that. And that's what Mr. Linus and I talked about too. So it prepares you well for your calculus. So you use for the format. And you're going to get part 2 questions that are like A, B, C, D, E. You have to find like 5 answers to them. So like I'm going to give you the first question, and then you're going to have to do like part A, determine this value. Part B, determine this. Part C, determine this. And they'll work successively. So it'll like build up on each other. Okay, so your part 2s won't just be one problem like this. You'll have like part A, part B, part C to the same problem. Okay? But it'll make sense. It'll be written in a fashion such that it's orderly, meaning like it goes in order. You'll find the first part, which leads you into the second part, which leads you into the third part, and so forth and so on. But if you get the first part wrong, right, and then you use your answer from the first part, which causes your second part to be wrong, I'm not going to give you both parts over both. So say you get the first part wrong, you get the answer is 5. And then you use 5 in part B. But you get the work right based on your incorrect answer, you'll still get credit for part B, because you did the work right. It's just that you happen to have the wrong answer in part A. Is that clear? And that's not always done on the AP test. I'm just giving you guys a little bit of a leeway. Alright, there's a 4th problem. I'm going to leave it for now, because what I want to do is take a look at the homework from section 1A. Okay, and I know you guys didn't look at this because I didn't ask you to, so I didn't expect you to at all. Okay, but what we're going to look at is one of these problems. The 1-9 homework, just so you know, that you're going to work on tonight, if you want to write it down while I'm doing this. If you want to see example 4 was a little bit complex, and after going through it several times, it might not be worth going through a problem this in depth right now, especially solution to this. This would be like an extremely difficult problem when it comes to SAT. One of the toughest ones at the end. But I did put the solution up and I wrote it all in my own words. I didn't use the textbook answer because the textbook answer was not written well at all. Okay? So if you want to go look in the notes before me, you can. This is going to be what you're doing, and it's not written exercises in this section. They don't call it written exercises, they just call it problems. Okay? So feel free to take a look and notice that. So,
Oh, that's what I was asking. I was, thought it just meant like problems.
not here, no, let's see. Okay. So let's take a look at another problem from section 1A. So we'll do. We're going to do number 6 on page 47. I want to write it down so later on you can refer to it. Page 47, number 6. This is section 1A. Page 47, number 6. So the problem says the following. The length, width, and height of a rectangular box are consecutive integers. So, that's how I would write it. The length, width, and height of a rectangular box are, and I'm going to make it tougher. Well, I'm going to deviate from the problem a little bit. I'm going to say they are consecutive, even integers to make it harder. And you guys saw this, right? In the video, I did an example with consecutive integers. Okay, this is another problem we're going to look at. Consecutive even integers. And the largest dimension is k. If the volume, and I'm deviating from the problem, just so you know, I apologize, I should have said it before. If the volume is, let's say, 450 cubic centimeters, then find each dimension. Find the dimensions. And when you get to calculus, you're going to do problems like this that involve what is called optimization. Okay? And you're going to learn to optimize about, given a certain amount of material, what shape should it actually be? What should the dimensions be so that you get the most surface area with the least volume, or the most volume and the least surface area? Those are called optimization. So a little preview for you. Can somebody give me a starting point for this kind of a problem? What's the starting point? And remember what kind of statements we should start by making. Okay? Don't forget to use K to start, right? Use the problem as. Close? Still close? Very close? How about?
No, I don't get it.
You have the answer? Can you give me the first step then? That's the question. What's the first step here?
Since this K is the largest dimension,
If K is the largest dimension, what's the next even number that's less than it? It's 2 less, right? Because 8, 6, 4, they go down by 2s. So if K is the largest dimension, we've got a K length, we've got a K minus 2, and a K minus 4. That's our first starting point. And
And then you would put 480, and then you would,
450, look at that.
oh, alright, and then you would.
What equals 450?
So then you would simplify it and you would, combine like terms.
Before we simplify though, I'm asking you, what am I writing? What is equal to 450? How am I writing? Good. Okay, make sure we multiply because I feel like some people might have tried to add these. Did you add it at first? Because you said add, and then you said combine like terms, so I was confused when you knew to multiply. Why am I multiplying? I'm going to answer that question. Again, why am I multiplying? Volume. And volume of a cube or some sort of rectangular solid is my most basic formula. If you don't remember it, it's all right. But volume is LWH. Okay? And that's something from geometry that you might not have learned yet, so I understand that. Okay, so on your test on Friday, if you're given a geometry problem, there's a good chance I will give you the formula. Because I didn't let testing on the formulas. Is that clear? Just to make sure that you don't get anything wrong there. Now, with that said, we have to solve this problem, don't we? And isn't this a little bit complex here? Does it look a little bit complicated? So, at this point in time, what might the next step be? What might the next step be? Summer?
Can you use foil on the tissue?
Yeah, I would do the same thing. Very good. I would foil the inside first, right? Leave the K alone. When I foil this, I'm going to leave the K out here. Summer?
K squared.
So we got, we're all familiar with FOIL, or box method, or double distributive, whatever you want to call it. This becomes K squared.
Negative 4K.
Okay, the outer is going to give us negative 4K. The inner is going to give us
Negative, well, that's negative 6K.
total. So outer, then inner will give us the negative 2, right? So we're going to have minus 4K minus 2K. This can be combined if you know that already, obviously. And then,
Positive 8.
good. And summer, remember, negative gives a positive. And that's last. Again, FOIL, first, outer, inner, last. If you remember, and you know it already, please, you don't have to write this separately. Just put that as a 6K and leave the negative sign right there. Okay, see the negative sign right here? And leave it as a 6K. Now,
K squared minus 6K squared plus 8K.
now, in order to solve this problem, I really need to move the 450 over. So Manny, what would the 450 look like on this side of the equation? It's positive over here, so it's, if it's positive on one side, if you ever move anything over, it's negative. Very good. Very good. Now, anybody remember from Algebra 1 how to solve this? Did you learn how to solve this? I don't remember if you did. Maria? You can try and factor, but it's cubic. So we can try and factor by like a grouping method if we can. Is there anything to come out of here? Well, K squared can come out of here. Looks like a number like 2 can come out of here. 4 can't come out of here. So it might be tough to factor this. There's a method to solve this. And you all have something that is a tool that you can use. It's about this big, rectangular, it's made of plastic. It's in your backpack probably. Okay. And I'm showing you a little bit of advanced technique. We're not going to do it until later in the year, but I want you guys to see that these kind of problems, they can still be solved even though they haven't gone through it yet. The easy way to solve a problem like this, the easy way to solve this is go to Y1. Hit Y1 and go to graph. Under Y1, type in this equation but use X's instead of K's. So you're going to have Y1 in your thing equals X caret 3. If you need help, ask. Y1 is in the upper left, and then clear it. Okay, so the upper left button is Y1, and then you clear it. Turn your plot off. Here. So your plot's on. So X is right here. So that you use X. Let me bring up my calculator actually. How much time do we have? About a minute. Let's see if the calculator here works. Hold on. My other computer has it. GI tools for workroom. So we're typing in this equation if you know already how to do it, but I'm trying to bring up the calculator to show you. Come on. All right, unfortunately it didn't work for us there, guys. Tonight, take a look at section 1.9. Okay, tomorrow we'll start with 2.1. We'll pick up with this tomorrow. Okay? We'll pick up with this tomorrow. You want to look under news tonight? I'll put a video up on how to do this in the calculator. Go to news on the news forum, and I'll put a video on how to do this on the calculator tonight.